Okay, friends, welcome back. We are on 15th module. Okay. In this particular module, we'll be looking at three additional search algorithms. One is called iterative deepening A star. You've already seen iterative deepening. Now we are going to see how A star and iterative deepening matches here. We'll have there is something called RBF or recursive best first search, and then we'll have an introduction to agents. What they are, let us see. You've already seen A star is a very popular algorithm, and because A star is very popular, a lot of others try to adapt to the characteristics or the good things of A star and learn better and become better. So, iterative deepening, we have already seen the iterative deepening. You start with root node, explore the first level, again start from root level, explore 2 levels, again start root 3 levels. Seemingly wasteful, but found useful, as I said when we discussed about iterative deepening, that such a thing, if we provide heuristic value with it, it becomes better. Okay, so IDA star is basically that. We'll be looking at IDA star first, and then RBF, okay, which is recursive best first search. Both of them are memory bound. They are known as memory bound searches. The memory bound, why they are called memory bound? Because they expect memory to be limited and are designed purposefully in a way that amount of memory that is required is always minimal. What we do is for RBF, the conventional depth first search, if you remember, it remembers unexplored node, list of unexplored node, list of explored nodes. Why it keeps a list of explored nodes? Because if an explored node is regenerated, it will find that thing out. Why it keeps unexplored nodes? Because it will pick up the best out of that and pick up next. Okay, so that it keeps. But in case where such lists are impossible to be kept due to shortage of memory, RBF like solution may be used, because which doesn't keep the explored list and only the best unexplored node is picked up. The advantage of this is that you don't need to require amount of memory that you need, and obviously the cost is that you may explore an explored node yet again. Okay, so that's the problem. AI is driven by lot of programs which are more or less automated, can interact with real world. For example, a program which books our tickets, the program which arranges our tours and all that on its own based on our preferences. So when you do things like that, the program acts on our behalf. When a program acts on our behalf, it is called an agent. In fact, if you look at intrusion detection systems, there are a lot of botnets coming up. Those botnets are basically softwares, a small software which goes to some other computer and acts on the attacker's behalf. Okay, so they are also examples of agents, and we'll be talking about, that's the third thing that we are going to look at in this module. We'll introduce IDA star and RBF star in short first, and then we'll move to agents. They were both, IDA star and RBF were proposed by a guy called Richard Korf, and he was working on, as a professor working on space complexity of algorithms, and he was interested in improving the cost of the solution path calculation. He was interested in reducing the amount of memory to be used. He assumed that the amount of computing power needed may be more, but the memory should be less. And he has devised these two algorithms. And there are three things that he wanted to optimize precisely. First, the amount of memory that is to be used, so the cost of finding the solution itself, and the path to the solution itself. And he was working on computational biology problem where the search space is like grid structure. So number of combinations and permutations become very, very large after a while. And when that happens, it becomes very hard for the algorithm to proceed further. The amount of memory that you need to store explored nodes, the amount of memory that you need to store unexplored nodes goes quite high, and because of that, that leads into trouble. So the IDA star, how it works, both IDA star and RBF, both has a linear space search strategy. That means the amount of search space at any given point of time increases linearly rather than exponentially, because in case of grid it increases exponentially. The number of paths that you require to explore at every point of time is exponential in normal case. In this case, it is linear, though that is the biggest achievement of IDA star. Obviously, it adds to the cost of, in fact, the same nodes are explored again and again, because you don't remember that this node is already explored, is going to add to that time. So that's a disadvantage of this algorithm. And in one sense, this IDA star is more near to depth first this limited search that we have seen in probably the fourth model. Now the idea is very simple. Remember DFDL. Okay, what does it do? It explores, it assumes the length to be some value. Okay, depth maximum 3 or 4 or 5. Now you explore that. If you reach there, you limit it. Okay, go back, act like you have reached to a dead end, and you go ahead and explore the search space for that depth only. Now in DF, depth first, depth limited, usually you start with length equal to 1, then 2, then 3, or you start with 3 and 6 and so on. Here, instead of that, it's quite interesting move is that you don't do that, you just use a G plus H dash. Take a specific value of G plus H dash. For example, you just say that G plus H dash to be 3. So what you do, you just start exploring nodes, and if whenever G plus H dash value goes beyond 3, you just stop and take a previous node and take the other branch and so on and so forth. So IDA star is very similar to DFDL. Okay. The only point is you just use G plus F. Now why G plus F is better? Because you know that if you traverse in the wrong direction, the G and H dash value will go high. So when the G and H value go high, the wrong direction you won't move further much. But the right direction, because G plus H, remember the case that we have seen in the previous module, G plus H was consistently to be 6, almost till the end. So those things where those nodes which are nearer to the solution, they are explored more. That region will be explored more. The regions which are in the other directions are not explored that much. That is the advantage of using this method. And if you don't get, what will happen? In most cases where SDET underestimates this, you probably will not get for the first time, because you estimated it to be 3, but it is actually 6. So you won't. So, but then once you do not get it, you can increment, you can pick up the best node so far and use that thing as the measure and again try. Okay. So you may continue doing that, eventually you will be able to reach there. So the example is shown in the figure. The white node is the starting node and the red node is the ending node. And you can see the green nodes which are inside the G plus H. So you can see that more number of nodes are explored in the right direction and less number of nodes are explored in the other direction. In the second iteration, you can see that more search space is explored, but you can see that search space near to the solution is explored more. That is the power of IDA star. So you can see that more number of green nodes traveled red node in both cases, more in case 2 than case 1, and nodes in the other than right direction get their H value higher in a much faster way. So you don't need to explore them more. And you can see that doesn't demand the amount of space A star needs. Why this is preferred in some cases. It uses optimized storage, but costly in terms of time. And the value, G plus H value that you use is called cutoff value. And that initial cutoff value is based on root's estimate, the H dash value. If H dash is optimal in this case, we will get an optimal solution. Admissible, then we get an optimal solution, like A star as here as well. If we don't get a solution, we will just increment. As I said, that we just pick up the best so far node and set that value as the cutoff value, and we will start working on it again. We might need to do it in multiple iterations, but if it is H dash is admissible, we sure that we will get it, we get an optimal solution. And the algorithm is also shown on the next slide, and we call that thing limit. Okay, limit is the cutoff value. So that limit equal to H dash root node. Now you assume that from root node, the 3 hops away, you will get a solution. Then that value is your cutoff value, the limit. And the current node is root node, and you start traversing like depth first says. As soon as the G plus H dash value goes beyond 3, you just stop, you go back and take the next branch and continue doing that. If you get a solution, great. If it doesn't get a solution, there has to be a best so far node. Now best so far node says that the goal is 4 hops away. So then you increment that to 4 and again do it, or 5, then again do it, and so on and so forth. So that's how you do it. If G plus H, as I said, G plus H is greater than limit, obviously will stop. Otherwise, if there is no node, find out, you change the limit value. Otherwise, add this node to the path. Okay. If node is better, best node is this node. If this node is not better, the older best node will continue. It's like finding on maximum a number in a given array. Okay. So that is how it is done. This is basically a DFS with heuristics. There are two different situations in this case. G plus H dash going above limit, and you calculated everything for all branches. When G plus H dash exceeds, you assume that there is a deadlock, dead end, and you won't move further. When all nodes are explored, you just increase your limit. But remember, when you increase, that does not mean that you will start from where you left. You start all over again. Now that is important. you just forget everything, and that is again a disadvantage of using idea star. It does not know that, otherwise it has to remember the complete branches of all the complete tree that we have explored, and we don't have the amount of memory. We do not want to use that amount of memory in this case. So that's why it will have to start again all over again from the same place. Okay, it reduces obviously storage requirement, but that increases time because of this, and though it is moving in the right direction, but there is no real sense of direction. It doesn't really know that the goal node is in that direction. It's just moving, just jumping in all directions and based on our g plus h dash value without really having the idea about the direction. But nodes are very well connected. It takes a lot of a time because it has to again look for all paths, though it'll have to do it again and again because it won't remember explored nodes. So that will take a lot of time, and it is better for less connected graphs. If it is well connected, it will take a lot of time, and that is not very good. Unlike the earlier case, the admissible function does not mean that it's the best function. The next algorithm is recursive best first search. Is like best first that we have already seen, but with one difference. In earlier case, the best first, what we do is we only store the complete set of explored nodes with set of unexplored nodes. Why we store the list of explored nodes? Because if we generate a new node which is an explored node, we don't need to worry about that further. It's kind of a cycle. Okay, so we will have to stop. Why we skip the unexplored nodes? Because we'll have to find out the best out of it, and then we'll have to choose one, the best one from it. So that's why we did that. In this case, the recursive best first search, we don't do that. What we do is we only pick the best, keep the best unexplored node, and we'll only explore that. And when you explore, actually, whenever I'm exploring my children and I find that no children is better than the parent, when there is no children better than the parent, what you do is you pick up the best so far. When you pick up the best so far, the second best will be the best child, whatever the best child that you have, because you don't have any other node. So that is pick up as second best, and you explore this. When you explore this, you find that these children are much higher value than this, then you pick up this and start. And at this point of time, the best child of this becomes the second best. So you only keep two values, best and the second best, and whenever you move from one value to the other, the best value becomes second best, and whatever value you move to becomes the best. Okay, so that's how it proceeds further. Like the other case, idea star case, it's like normal depth first search. Okay, the best node is explored, but second best is preserved. It won't preserve all other nodes, only second best. And if the best node is explored and all children are found to be worse, the search process backtracks to the second best. Okay, so on and so forth. I have already discussed that. Now with that, we have studied two things: idea star and recursive best first. Both of them are memory bound searches. Both of them are good searches for space constrained problems. So whenever there is an issue with space, either of the algorithm can be used. But otherwise, they are not good algorithms for cases where the time is paramount. In most cases, it is so. So in that case, some other algorithm is used. In fact, there are many alternates provided by many others. Instead of just keeping one node, you just keep the nodes which you can fit in the available memory is one solution. There are a lot of similar solutions provided. But anyway, both the algorithms give us a very good idea about what people can do when there is a space constraint. So in fact, it is quite possible that there are other algorithms, and there are other algorithms which are generated from some other cases which uses the characteristics of these two algorithms. These two algorithms are not used in serious practice, but some other algorithms are inherited from this algorithm which are actually used in practice. The next thing that we are going to look at in this particular module is called agents. Now what are agents? Agents are software or hardware routines or programs or devices or whatever which works on users' behalf. A ticket booking agent, for example, is a manual agent. So what you do is you say, I want to move from Ahmedabad to Mumbai on this date, and I would prefer a second AC, so get me a ticket. I will do that. He'll look for trains, he'll look for timings and all that. Look at my preferences. I am probably have provided my preferences. I prefer a window seat. I'll prefer, if I'm traveling by day, I require a chair car. Night, I'll require 3 AC and so on and so forth. So whatever the preferences are, I'll book tickets accordingly. So that is the job of an agent. You provide your preferences, you provide what you want to do, and the agent does that thing for you. So agents are the programs which work on user behalf, you probably will be thinking, why I've started talking about, suddenly jump to an agent. Okay, we so far has talked about AI and programs which are difficult, and state spaces, neural networks, and many other things, and we have not yet talked about agents now, and we are just jumping onto it. What's the point? Why we are talking about agents? Anyway, when we talk about a search algorithm, or for example chess playing program, or a self-driving car, or whatever, eventually the solution has to exist in real world, has to connect with the real world, communicate with the real world, send something, receive something from the real world, and actually be a part of real world. And if you want it to work that way, the concept of agent comes handy, because agent is basically something which works on user's behalf, or the programmer's behalf, or the designer's behalf, and do exactly what they say, and interacting with the rest of the world, doing things with the rest of the world, requires it to solve the problems like we are doing so far. Okay, so that's basically the same thing which we are talking about. The only thing is that we have become more explicit now. We are talking about the real world case. So far we just say that chess playing algorithm is doing this, but we have not actually said how chess playing programs will work, how self-driving cars will work, how work to find out shortest route between two places. The agent, railway ticket booking agent, or real estate agent, even intrusion detection agent, they work the same. They work on user's behalf. What they do is they interact with the world. For example, intrusion detection system is the world of intrusion detection system is the computer address space where it runs, interacts with other processes, figuring out whether a process is malicious or not, and take the decision. It takes something from the world, it gives something back, and so on and so forth. So it's basically an extension to the discussion that we already have. The search spaces, the method to find solutions, and all that are really implemented using agents. A trip advisor is another example. A trip advisor is going to advise you about a trip. For example, you say that I want to plan a trip to Manali with my family, and the trip analyzer, looking at the preferences, will look at the possibilities of booking, the hotel booking, the dates and all that, even my budget and other information, and will do all that for me. This is basically a software agent. Compared to that, a self-driving car which let me travel from one place to the other is not only a software, is also a hardware. So it's hardware plus software. So agents may be hardware, agent may be software, agent may be hardware plus software. So these are the examples of agents, and they are using whatever we are discussing so far is actually being used by agents. So they are explicit versions of what we are talking. Another example is a parking sensor node which looks at the car being parked and decide whether the car is being parked properly or not, and start beeping when it is not, so and so forth. There are a lot of IoT devices appearing in this world right now. Okay, house monitoring system and smart agricultural system, and the implantable medical devices which looks at the body temperature and the blood sugar level and blood pressure and all that. So these are all examples of sensors which are taking some inputs, generating some outputs, and also processing using AI. So our discussion actually is confined to agents which think intelligently, which has to take decision based on things that we have talked about. Obviously, people call the agent with hardware plus software as physical agents, and the agents only containing software are called software agents. And I've told you, the world of agent is different. For example, intrusion detection system, the world of an agent is the operating system in which it runs, or the network in which it runs, and the processes which it interacts with, and so on and so forth. That's called the environment of the agent. A self-driving car, the environment is not itself, but the roads, the other vehicles, people who are using that car, and so on and so forth, other pedestrians, other vehicles, everybody who is there on the road and comes across when using this car, and so on and so forth. Point is, environment is the world for the agent, and in most cases the agent world is confined to a small area, and that is called environment. So whenever agent sends something to the world, it uses something called actuator. When agent receives information from the world, it uses something called sensor. So agent has two components: sensors which takes input from the world, an actuator which sends signals to the world or does something in the world or the environment. the processing done in the agent itself. So, agent interacts with the environment using the sensors. And so, agent does many things with the input. For example, it takes input from the real world, process them, store them, reason with them, generate output. Agent environment is something where the agent works, and not all cases agent, in most cases agent's world is confined to a very small subset of the real world. How agent works? For example, an intrusion detection agent, look at some input patterns observed, it looks at what is coming up and decide whether it is an attack or not. If it is an attack, it sends the signal somewhere. If it is not an attack, it let it go. So, the information that it gets is called percept. For example, there was a very old attack called land attack, where the sending IP address is same as the receiving IP address. So, if what does the agent do in this case? It looks at the current percept or the current packet that it is looking at, current observation, and it finds that the source address is same as the destination address. It decides that this is an attack and it drops it. If it is not, it will let it go. Now, it does not need to look at other percepts, it only looks at the current percept and done. Now, there is a complicated agent, little more complicated agent, which looks at whether the user, there is one more indication of intrusion, that there are a lot of failed login attempts. Normally you fail to log in once in a while. In 5, 6, 10 days, you probably fail to log in once. On one fine day, if the system find you failing to log 50 times in an hour, now that is a serious thing. Now, that is something very different, and I want to capture such things. So, I start running an agent. So, that agent does what? Can it only look at current percept and decide? It cannot. It has to look at percepts of last 1 hour and try to figure out how many failed login attempts happen. When it does that, it will see that it crossing value 50, it let me know. Okay, you can decide that value is 50 or 10 or 5, whatever. But here the difference is that it has to look at not one current percept, but previous percepts as well, and that is called percept sequence. So, agent can take decision based on current percept, which is simpler agent. Agent may take decision based on the percept sequence. Okay. And conventional old intrusion detection systems were like virus scanners. You just look at the packet and it finds that the packet contains something which raises the suspension. It says that suspiciousness, and then it just pick up that thing and drop it. Okay. So, just looking at the current percept, it decides. If it is not found that, let it go. But then, as I said, there is a simpler methods. This signature recognition is always based on current percept. But then there is a stateful kind of a situation where it looks at multiple states, knows what has happened before and all that. So, it remembers all that percept sequence and take a decision. Is a complex case, and sometimes you are learning how a user is behaving and make sure that the user's behavior remain consistent. If there is inconsistency, you just report. For example, as a normal user, I will hardly access system files. On one fine day, I just start downloading all system files, and that is something suspicious. So, that kind of thing also can be looked at, but for that I need to find out the normal behavior. So, for which I will have to read a lot of percept sequence, probably a day or sometimes even a month, to figure out what the behavior of that user. So, for that, this percept sequence makes a lot of sense. There is one more word, rationality is attached to agents working. Now, how do you know that the agent is working well or doing a right job? One answer probably is, it will decide based on the output. If the output is good, the agent is doing a real job. If the output is not good, the agent is not doing a real job, a good job. But then it is not very good. For example, if I have designed a chess playing robot, that chess playing robot is playing something and take a silliest move, but the opponent tops the program by taking a sillier move and lost, do you consider that that move was good? Or the other way around, if the move the chess player program has taken is really good, but the opponent is very, very good and eventually could defeat. So, will the agent consider that the move is not very good? No, in either of the cases it is wrong. There are many other cases depicted in the handout as well as the PPT. One is self-driving car. If you are traveling in the right lane and somebody comes from the wrong lane and just meet with an accident, that does not mean, or crushes you, does not mean that you have taken a wrong decision by riding in the right lane. So, that kind of situation. So, you do not need to measure agent's performance looking at the output, but the better idea is to look at the objectives, and as long as the agent's working is based on the objectives. For example, user convenience. So, self-driving car, if the user is convenient, it reaches through the destination, the time, and feels comfortable. Not only the user, the person who is sitting in the car, but others, the fellow travelers also find that it is fairly doing well. Then these are the objectives that the agent has to meet. So, when the agent is meeting the objectives, we consider the agent is doing things in a rational way. Sometimes this is called credit assignment problem. Now, if you have done a good job, how will you assign that? Which move you think is responsible for this? And there are many factors which affect outcomes, which I have discussed. We cannot decide the rationality of the decision based on the output. We only decide whether it is the agent has followed our objectives or not. And I have taken few objectives. One, you take a sudden turn and go to a street which is full of traffic is a very bad decision. Okay, you may reach to the destination faster, but that's not a good decision at any cost. That's an example. And one more thing which you require in an agent is learning, the ability to learn. Usually the agent starts with minimum amount of knowledge, and over the period of time it learns. Okay, from the episode is called episodes. From episodes, agent tends to learn further and further, which is quite similar to what we have discussed earlier. There are three things. In fact, it learns from how the information that the designer has provided. Second, it infers from that input, whatever. And the third, it learns from its own experience. So, these things are important. With that, we come to an end of this particular module. In this particular module, we have looked at three things, two algorithms. One is IDEA star, the other one is RBF. Both of them are memory optimized algorithms, and this particular, the third part of this module is about agents. We looked at software and hardware agents which work on behalf of users, and we have also seen rationality in making a decision is very important thing for agents. With that, we conclude. Thank you.